Finally, we get to apply special relativity to our ideal scenario. As before, identical masses, zero initial velocity, equal but opposite acceleration at any given time results in equal and opposite velocity at any given time. Resulting in the same potential energy at any given time, because there is no time component with potential energy, and work between any given time increment. And of course, kinetic energy and change in kinetic energy are a factor of velocity. To verify that the shortcut of applying a time factor to mass is a mistake, let's do it. In the previous universal gravitational equations, where the primary mass is much greater than the secondary mass, adding a time factor to the secondary mass results in the same acceleration. However, when applied to a time factor to both of identical masses, the result is that only one of the two time factors is cancelled, and both masses accelerate faster towards each other than predicted by Newton. Since Einstein's equations, when properly applied, results that the objects accelerate slower than expected by using Newton's equations, clearly the Lorentz time factor cannot be applied to mass. By definition, the Lorentz time factor is change in observed time divided by change in experienced time. Therefore, the change in observed time is a product of the Lorentz time factor and the change in experienced time. Mass A equals mass B equals mass. Acceleration of A at any time is equal to the negative acceleration of B at the same time, and the same for velocity. And the sum of two identical kinetic energies is simply mv squared. While the change in observed time during the descent is the same for the ascent, they are greater than the Newtonian time, which means that while the observed velocities for the descent equals the ascent, they are less than the expected Newtonian. Likewise, the change in kinetic energy experienced in the descent and ascent, while identical to each other, are less than the Newtonian. It's as if some of the kinetic energy was transferred into time dilation during the descent, and the time dilation returned to kinetic energy during the ascent. It's as if it's dependent on observed distance being equal to the experienced distance, which will not be valid once the maximum speed of light is applied to the velocity of gravity. This will be explained in a future video. This results in zero net loss if there is a bounce or a slingshot. However, because the relativistic kinetic energy observed is less than the Newtonian kinetic energy experienced, according to potential energy lost, if there is a collision, the energy that was transferred into time dilation will be permanently lost. To demonstrate this, let's look at the first documented gravitational wave, GW 150917, detected on the 17th of November in 2015. Don't worry, the decay will be explained in the following videos. A chirp signal is an event lasting 0.2 seconds when over a period of 8 cycles, the signal frequency increased from 35 Hz to 250 Hz in the 200 millisecond, entering the audible range. At an orbital frequency of 75 Hz, which is half the gravitational wave frequency, the two objects were orbiting each other at a distance of only 350 kilometers, traveling at 300% the speed of light. Please note the discrepancy of 62 solar masses for the final mass, when compared to 65 solar masses for the sum of the observed masses just before the merger. By applying the Lorentz and momentum equations to observed values of A and B, we obtain experienced values for these two objects. Individual observed momentums give individual observed velocities, which give individual time dilations. These personalized dilations are used to convert observed mass to rest mass for both objects. The results summarized in the following chart. As a bonus, I've included personal experience velocity, which will be valuable in future series. First thing you should notice is that the total rest mass of 62 solar masses is identical to the final mass after a merger. This agrees with the fact that gravity is not a force. Gravity does not transmit energy, nor does it require energy. Space-time is not a single fabric, but rather every object has its own perspective based on their velocities. Therefore, observed velocity is not experienced velocity, and observed mass is not rest mass. While counterintuitive, by recognizing that observed mass is an illusion, makes it easier to comprehend that the kinetic energy transferred in the time dilation is permanently lost during a collision. Since I'm only interested in comparison analysis, in my shortcut, I entered solar masses for mass and velocity as a fraction of c for velocity, so these values are not Newtonian. The actual potential energy used by the black holes at GW 150917 is the total experienced kinetic energy gained, 3.11 units, based on experienced mass and experienced velocity. This is the actual energy inputted into the system and explains why infinite energy is needed to accelerate anything to the maximum speed of light. The observed kinetic energy is slightly less, 2.96, because although all the momentum is converted between experienced and observed, the momentum based on velocity, while kinetic momentum is based on velocity, while kinetic energy is based on velocity squared. The rest kinetic energy, 2.81, is based on the rest values, is the energy available at the final merger. The difference between the actual value entered and the rest value that is ultimately available is the value of energy lost due to time dilation. And as I alluded earlier, once the maximum speed of light is applied, the velocity of gravity observed distances are different depending on the velocity of the observed object and the velocity of the observer, making space-time multiple individual fabrics.